So today's lesson, we're going to go over Kirchhoff laws, and we're going to analyze circuits, both parallel circuits, series circuits, and even mixed circuits, which are a combination of the two. So first, Kirchhoff was a German physicist in 1845, and we have a couple different laws that we're going to use, Kirchhoff's voltage law and Kirchhoff's current law. So the voltage law says this: if you have a series circuit, so take this series circuit that has a battery and 3 light bulbs, it means that the voltage through each light bulb sums to give the total voltage provided by the battery. So what that means is if the battery is a 6-volt battery, and these are all identical light bulbs, they'll each be 2 volts. Even if they're not identical light bulbs, you could have maybe 3 volts, 2 volts, and 1 volt. The point is that they must all add to be the same as the battery. Okay, so you can think of it as if you have an electron that picks up energy at the battery, that electron has to pass through each single light bulb. So it's going to give up all its energy, but it has to share it among those 3 light bulbs. Now, if you have a parallel circuit, Kirchhoff's voltage law says that the voltage given to any electron at the battery is equal to the voltage lost at each bulb in our parallel circuit. So if the battery gives any electron 6 volts, this will also use 6 volts, this light bulb will also use 6 volts, and that light bulb will also use 6 volts. So think of it as following a single electron that picks up a certain voltage at the battery. Well, that single electron is only going to go one of these 3 pathways, and so it will only pass through one of the bulbs. Other electrons will pass through other bulbs, but each electron only passes through one bulb. And so it gives up all its energy at that one bulb. Okay, so let's try to take this concept and do the first problem on our handout. So question number 1 says calculate the potential difference V2, so this one, in the electric circuit given. Now this is a series circuit, so because it's a series circuit, all of your voltages must add to this one. So this one is 240 volts. So that must be equal to 80 volts plus whatever this is that we're trying to solve for, V2, plus 60 volts. So now what we're trying to do is just solve for V2. I'll use a darker color so it's easier to see. So 80 plus 60 is 140. And if you subtract 140 from both sides, you will get V2 equal to 100 volts. Okay, so 80 plus 100 plus 60, then add to 240. So we're good. Next is Kirchhoff's current law. Now these laws are the opposite of the voltage laws, meaning if you have a series circuit, instead of adding, they're all equal. So the current that goes through the battery is the same as the current that goes through the first bulb, which is the same as the current that goes through the second bulb, which is the same as the current that goes through the third bulb. And you can think of it like a river. So you have all these electrons in this electron river, and that river, the entirety of that river passes through every bulb. Whereas if we have a parallel circuit, that river must split. some of it will go down this pathway, some of it will go down this pathway, and some will go down this pathway. The majority will choose the path of least resistance, but they will split. And so the current that goes through the battery must be equal to all of these currents through each bulb added together, because they will eventually come back together. Okay, so let's try a problem with the current law. 2 and 3. Question 2. Calculate this here, I3. So this is a parallel circuit, because you can see the pathway splits into 3 possible options. So if our total is 12.5 amps, that must be equal to all these added together. So 2.5 amps plus 4 amps plus our unknown I3. So now we're just trying to solve for I3. So we can simplify a bit. This will be 2.5 plus 4 will be 6.5. Then if you subtract 6.5 from both sides, you get I3 to be 6 amps. Now we're going to look at example number 3. This example, let me zoom in. This one's a little bit more tricky. You might look at it and say, well, is it a parallel or a series? And, well, it's both. This is called a mixed circuit. Here, the current definitely has to go through this resistor, but then it splits here, and then it comes back together, and then it splits again. So this one might be a little confusing, but we're going to go over it using the 2 Kirchhoff's laws. So it says find the unknown value. So what's unknown? Well, we don't know this current. We don't know this voltage. And we don't know this voltage or this current. So those are the things that we don't know. All right. Let's follow the current first. Let's follow the river. So if we follow this river, all the current is going through here. So this has all the current, and then that current splits into this and this. This side has 2 amps, and this side has 4 amps. So if something split into 2 and 4, then what split into it must be the sum of 2 and 4. So this must be 6 amps. And so we had 6 amps, which then split into 2 and 4. And then they came back together and then split again into 5. And, well, the other one must be 1 because it will add to 6. So 1 amp. And so there's our Kirchhoff's current rule for this mixed circuit. All right, voltage may seem a little bit trickier, but we'll follow it through. Now we have a total here of 72 volts. So we have a total of, I'll write this down, 72 volts. Now as the electrons pass through this circuit, let's just follow some electrons. They must add to this. Now, one electron will definitely have to go through this resistor here. So, it's going to use up 36 volts. So, we've used up 36 volts. So let's just write that down. Then, it's going to come here. Now, this says 20 volts. And this is something that we do not know. But Kirchhoff's voltage rule says when you hit a parallel circuit, the voltage is going to be the same. So if this is 20 volts, this must also be 20 volts. Now any one electron will pass through this, 36 volts, and then either this or this. So it'll use up another 20 volts. Then, if we're just following one electron, which passes through our first resistor and then one of these two resistors, that electron now needs to pass through one of these two. But in this case, sorry, I missed this one, we don't know either of the voltage, but we do know because it's a parallel circuit, they must be the same. And as this is the last resistor our electron is going to go through, whatever this is, let's just call it V, whatever that V must be, all of these must add to 72. So we can solve for what that V needs to be. 36 plus 20 is 56 volts plus our unknown one, let's call it V unknown. And that has to equal to 72. If we subtract 56 from both sides, we get that our unknown V is 16 volts. And that'll be the same for both of them. This will be 16 volts, and this will be 16 volts. Okay, pause. All right, so we've talked about voltage in a series and parallel circuit. We've talked about current in a series and parallel circuit. Now we're going to talk about resistance in a series and parallel circuit. Specifically, what we call equivalent resistance. So equivalent resistance means that, let's say you have this circuit that has 3 resistors. Could I replace all 3 of those resistors with just one resistor that would be equivalent? And that is what equivalent resistance means. It would also be the total resistance that goes through the circuit. Now, in a series circuit, if you have resistors in series, the total resistance or equivalent resistance for an equivalent resistor is the sum of these. Okay, so if this is 20 ohms, 20 ohms, and 20 ohms, then your total is 60 ohms. Now, for a parallel circuit, it gets a little bit more trickier. The mathematical relationship says that 1 divided by that total equivalent resistance equals 1 divided by this resistance plus 1 divided by the second resistance plus 1 divided by the third resistance, and so on. And those are all fractions, so you can't just take the reciprocal of those. Okay, we'll do an example where we have to solve those. Okay, well, 2 examples, so 4 and 5. Question 4. Question 4 says, what is the equivalent resistor in a series circuit? So we have a series circuit containing a 16 ohm, 27 ohm, and 12 ohm loads. So in a series circuit, our total resistance is equal to R1 plus R2 plus R3. So we're just going to add these. So we have 16 ohms plus 27 ohms plus 12 ohms. Okay, so you get 55 ohms. So series circuits are not so bad. Let's look at example 5, where we're going to have a parallel circuit. So find the equivalent resistor when, so we have a 4 ohm and an 8 ohm bulb connected in parallel. So in this case, our total resistance would have to be 1 over your total resistance equals 1 over that first resistance plus 1 over that second resistance. So we have 1 over RT equals 1 over 4 plus 1 over 8 ohms. So if you like working with fractions, or if you just want to use your calculator to plug in 1 over 4 plus 1 over 8, that's fine. 1 over 4 is the same as 2 over 8. That's an equivalent fraction. And now that the denominators are the same, 2 plus 1 is 3. So you would get 1 over R total equals 3 over 8. But, this is very, very important, do not stop there. That is not your final answer. Your total resistance does not equal 3 over 8 ohms. What you solved for was 1, I'm going to go rewrite this over here. You solved for 1 over RT equals 3 over 8. And ohms is on the denominator. What you need to do at this point, you can take the reciprocal of both sides. You couldn't do it before because you were adding two different fractions on one side. But now we have one fraction equal to another fraction. You can simply take the reciprocal and flip them. So you would have RT over 1, which is just RT, equals 8 over 3 ohms. Notice that 8 over 3 ohms, if we were to write that as a mixed fraction, that is 2 2/3 ohms. Now for this unit, I'd prefer you keep everything in fractions because it'll help be more exact with all of your laws when solving circuits. Okay, so try not to use decimals. If you need to use your calculator, that's fine. But what I want you to notice, there's two differences. First, look at our series circuit. The total resistance is greater than any individual resistor. So 55 is more than 16, which is more than 27, and it's more than 12. Not true with a parallel circuit. Here we have one resistor is 4 ohms, another is 8 ohms, and the total is less than either of them. All right, so let's move on to question number 6 then. Question number 6 is a mixed circuit, and we're going to calculate the total resistance. So we're going to have to use both of those laws, the resistance for series circuits and the resistance for parallel circuits. So here we have 3 resistors in parallel. So remember I talked about not necessarily total resistance, but how you can an equivalent resistance. So I can replace those 3 resistors with one resistor that is equivalent to those 3. And then when I do that, our circuit will then look like this. We have our 1 up there. We have our equivalent resistance here. I'll call it REQ from these 3. And then we have our R5 down here. So this would be 12 ohms from up here. Down here would be 18 ohms. And here is REQ. Now this circuit is a nice simple series circuit. So if I wanted to figure out that total resistance, all I had to do is add those 3. But before I do that, I need to figure out what that equivalent resistance is. What resistor can I replace those 3 resistors with? To do that, we're going to have to use our law for adding resistors in parallel. To add resistors in parallel, we're going to do 1 over REQ equals 1 over 75 plus 1 over 50 plus 1 over 30. Now if you added all these on your calculator, then you'll get 1 over 15. That is not the equivalent resistance. You now need to take the reciprocal of both sides to get Req equals, right? So when you flip this, you get an equivalent resistance of 15 ohms. So now we know this is 15 ohms. Once we know that's 15 ohms, we can easily figure out our total for a simple series circuit by simply adding those three resistances, 12 ohms. All right, so let me just recap this question because we're going to do lots of questions like this. Whenever you have a complicated mixed circuit, what you're going to do is look for areas where you can simplify it into a nice simple circuit that you can solve. Once you've simplified this into an equivalent resistance using the laws that we learned, then you have a simple circuit where I can just add those resistances to get my total resistance. Now next time we're going to do problems with mixed circuits where we're going to put everything together, resistance, voltage, and current, and we'll go over a sort of algorithm how to do that. And I also have a sort of an animation video that I created which goes over a complicated mixed circuit that's on the Google site. Okay?